hydroxide ion promoted hydrolysis of the ester shown below. And the ester shown below has been labeled with a heavy isotope of oxygen. So we've got an oxygen 18 label in here. And so we're being asked which hydrolysis product will contain that label. So this is getting at the mechanism of this reaction. This is really what we're being asked to focus on. So this is focusing on the mechanism. Right, so if you have a hydroxide ion promoted hydrolysis, you'd be doing a first step with hydroxide to do the hydrolysis, and then you always do an acidic workup to put the proton back on. So that would be a second step. And you might see in this first step that it would go faster if you heat it up. Don't let it throw you off that it doesn't say heat. It's still telling you that this reaction works, so we're assuming that it works. So when you hydrolyze this, you're going to get two products. You're going to get the carboxylic acid, and you're going to get the alcohol. And so this question is asking us the fate of this oxygen atom, right? So this is the one that we're focusing on. So we want to know where that ends up. If we draw the mechanism, that should tell us. So when you have a base-promoted hydrolysis, your base is a strong nucleophile, right? Because it is hydroxide ion. And so that strong nucleophile is going to attack the electrophilic carbon and then break the pi bond, pushing the electrons up onto the oxygen. And so the result of that is a tetrahedral intermediate. So we have broken the pi bond, so we have an extra lone pair on that oxygen. We have the hydroxide ion that we have added, and we have the OR group. So I'm going to make sure I put the label on that oxygen because that's the one that we're focusing on. We want to see what happens to it. Okay, and so this is your tetrahedral addition intermediate. And so what happens from here, if you have a good leaving group, is that your electrons can come back in and they can push off the leaving group. And now you can actually push off the OH or you could push off the OR group. So it's an equilibrium reaction. We would design the conditions to kind of push the equilibrium forward. And when we draw the mechanism, we're assuming it's going in the forward direction. So we are going to kick off that OR group. And so here's where we cleave the bond to that oxygen 18. So this tells us that then we have a carboxylic acid, and we have the alkoxide, and that alkoxide contains that labeled oxygen. All right, and so this is really enough information, I should put the negative charge on there. This is enough information for us to be able to say that B here is the right answer. For completeness though, I'm gonna quickly finish this mechanism because this is a base, this is an acid. They are going to react with each other whether you want them to or not. So the next thing that's gonna happen is we can grab that proton, and this could equally be as likely to have another hydroxide if you happen to have one in the proximity of that carboxylic acid, could also deprotonate. So this is going to give you the carboxylate and the alcohol that contains that label. And so this is where the reaction will sit until you add in acid. So that's why we need acid as a second step when we have this reaction taking place under base promoted conditions. So just to get that neutral carboxylic acid in the last step, you need to have added a proton source so you can do this protonation rate here to get to the carboxylic acid.